Good day, everyone. I just want to make a video quick on David Lynch and his research into proving that there is a curve. Now, I found it quite interesting when I was researching and stumbled upon David here that he actually goes way back. As you can see here, he had his astrophysics in 1969. Again, a marker year. If anyone follows my work will know that I look at certain years with the possibility of 666 in them. They seem to be the marker years to all the incidents we see or people's professions and so on and so forth. But that's a whole different topic. What this is about some of his research that I've stumbled into. Now, I'm going to post links to this, plus I'm going to hold a stream on my other channel tonight to go into detail over this. So this is going to be a quick summary, just to quickly bring it to your attention and for others to start researching David K. Lynch. So I'll post this link to his page. One other thing to take note is David Lynch worked for the Aerospace Corporation. This was last updated back in 2001. The research we'll be looking at is after this time frame in his life, in 2005 and 2008, I believe, is when he posted some papers to the scientific community. So we'll go over those. One thing that he was famous for was studying the San Andreas Fault. So it's a good thing to go into. Also, his connection with NASA is another thing that we want to research. He has many papers devoted to NASA and their research. So I'll have that link here as well. Some of his presentations that he does I'll go through just a few here, is the field guide to the San Andreas Fault, like I said, is most well known for. Color and Light in Nature, the whole shebang, presumably over the Big Bang, right? Intelligent life in the universe, asteroid impacts on Earth, tides, pulse of the planet. So those are some of the presentations they have listed here on his website. Now these are all the papers that they list here on his one website, and they date back to 1981. The papers I'm going to quickly go over are this Visually Discerning the Curvature of the Earth, and that was done in 2008, and an earlier paper, Turbulent Ship Wakes, Further Evidence of that the Earth is Round, and that was done in 2005. So let's just first, I want to go over the Visually Discerning the Curvature of the Earth. And in this paper here, I'm going to have a link to it. The introduction I'm just going to quickly read. The first direct visual detection of the curvature of the horizon has been widely attributed to Auguste Piccard and Paul Kifner on 27th of May 1931. And we know that we've researched that. He went up, and that was in a scientific or Popular Science magazine. There's an article on that you can research on YouTube. They reported seeing it from a hydrogen-filled balloon at an elevation of 15,787 meters over Germany and Austria. On November 11, 1935, Albert Stevens and Orwell Anderson became the first people to photograph the curve. They were flying in the helium-filled Explorer 2 balloon during a record-breaking flight to an altitude of 22,066 meters over South Dakota. Other claims have been made as to being the first to see the curvature of the Earth, but they seem to have come long after visual curvature have been established. Since that time, countless people have claimed to be able to discern the curvature of the Earth as an upward arched horizon from high mountains or commercial aircraft. Now that's quite interesting, because Augustus, as we all know, had said the same thing when he went up, is that at the horizon the Earth seemed to curve up, not down, which you would expect if you're on a spherical Earth, right? And then it continues on here. We know that if we get high enough, i.e. from space, the curvature of the Earth is evident. But commercial aircraft seldom exceed altitudes of 40,000 feet, as we know, except for some other aircraft, which will be mentioned here. Interviews with the pilot and high elevation travelers revealed that few, if any, could detect curvature below about 50,000 feet. And that's, I mean, Tyson even mentioned that, right? Gotta get high enough. And it's been our argument for a while now, like how high do we have to go? And that's where this paper comes extremely important, because we're going to actually get a measurement to where they say the curvature should be apparent from that altitude and above. And I want to go over that, and we'll go over in detail later in my stream. But I need to get this out there to everybody, because this is a documented paper that was received, is at Harvard, is within the scientific community, and it has our measurements. So let's continue on here. High altitude physicist and experienced sky observer David Gutierrez reported that his B-57 ascends. The curvature of the horizon does not become readily sensible until about 50,000 feet. And that at 60,000 feet, the curvature is obvious. So here we have a pilot saying at 60,000 feet, it is obvious. And we have footage from above that altitude with our high altitude balloons. They go up to anywhere 100,000 to 120,000 feet up. Having talked to many other high flyers, the S-70 or SR-71, U-2, spy plane, etc., Gutierrez confirms that his sense of the curvature is the same as theirs. Passengers on the Concorde that flew at 60,000 feet routinely marveled at the curvature of the Earth. And that's interesting, because I went and reviewed a lot of the footage from Concorde, and all the footage I've been able to find shows a flat horizon. So this is incorrect in my opinion. So we go on here. Now Gutierrez believes that in the field of view, the FOV is wide enough, it might be possible to detect curvature from a lower altitude. The author has also talked about many commercial pilots, and they report that from elevations around 35,000 feet, they cannot see the curvature. Okay, now field of view is the field of, like, below you, of what you can see until the horizon. Now, one thing we've got to consider is, if you're standing on the ground, on a level ground, and you look up to the horizon, it's about 3 miles you can see to that horizon. Now, the one thing we don't talk about, but we should investigate more and see more of in our videos, is we should talk about the distance to horizon at these higher altitudes. Around 35,000 feet, the horizon will be about 240 miles away. Now, when we consider that, then that means the field of view in front of us is about, because we can see about that 60 degrees, is about 240 miles square. So if we do our curvature measurement, we should see a visible curvature just in that field of view, you know, and that's a big argument in my opinion for us. But nonetheless, that's just a side note. What I want to really look at here is this 35,000 to 60,000 foot range, where we seem to get discrepancies with pilots in that. So I'm going to go into detail, like I said, through the stream. So I'm just going to skim over and explain some of the stuff that's been mentioned here. The first thing he gets into is about pictures taken from sea level and 35,000 feet. That at sea level we get a sharp horizon, and then when you're up any type of altitude above 14,000 feet, roughly about there, I believe he says, you start to get it to dissipate, to kind of get area of haze that you can't discern where the sharp edge of the ground and the horizon or the sky meet up at the horizon. And they prove it with an experiment with 2 photographs taken, and they show where the sharpness is at one and the other one is just beyond it. It's not discernible. So remember that for up here. Another thing to take note in this is it goes over the argument about the photographs and footage we do see. And we know, as flat earthers, we've been able to discern about the fisheye lens. Now he goes into great detail about cameras and their lenses being that they all experience a barrel distortion. Now barrel distortion, what happens is you have to put the horizon dead center of your frame, because if you're to tilt it down or tilt it up, you're going to be causing a convex or concave horizon. And he goes into this and he says, you know, about 95% of the people that do see the curve, it's due to this problem, that they're tilting their cameras. And then again he goes over some more examples here where the horizon's put in the center of the frame, the camera's lowered, gives you the curve, and it's raised, gives you the convex. Again, some examples here, and this is all documented by David, who is a well-respected scientist as far as I can tell, from Harvard, NASA, Thule, all these universities, Cambridge. So to me this is very documented scientific evidence that we could sit on and work from, because this is what the scientists are telling us. So when he also was up in an airplane, and this is where he talks about around 14,000 feet and such with these pictures. Again, but where I wanted to go into, and we'll discuss this, like again I said, tonight in the stream in detail, but I'm just going to quickly browse over this picture, is that he's going to try to prove curve here in this paper by taking a high altitude shot, so around 35,000 feet, and then he takes Photoshop or a program likewise to draw a line across it. And remember he was saying up here about that there is no sharp horizon at that altitude. So what he's done here, if you see, is that line comes down by 1-2 pixels, 2 spots here it shifts, and he's saying those 2 little shifts, this here, it proves the curvature from a 35,000 foot shot at the horizon. But if you really look, you can see he's angled his line down from the true line of the top of the haze. So if we were to straighten it up, it would take out those 2 pixels in my opinion. So that's another thing we're going to be discussing tonight. So, you know, in his conclusions here, summary and conclusions, I'm going to read this quick. In view of the agreement between the visual observations, measurements of the photographs, and the theoretical curvatures, it seems well established that the curvature of the Earth is reasonably well understood and can be measured from photographs. Interesting, right? The threshold elevation for detecting the curvature would seem to be somewhat less than 35,000 feet. And again, I say the threshold elevation for detecting curvature would seem to be somewhat less than 35,000 feet, but not as low as 14,000 feet. So photographically, curvature may be measurable as low as 20,000 feet. Crazy, eh? So we're getting some measurements here that we can use that are documented by a scientist that has submitted this paper for review and accepted by the American Optics Society at the time. And he goes in here, like I said, I'm going to go into this more in detail. It's interesting, he brings up the density again. He talks about the air vapor and stuff in the air. He also talks about a true horizon. Now, it's quite interesting how they do their calculation to see what the difference of curvature is, because they base it off of the true horizon and then down, right? So that's something we'll go over tonight, because we're going to go through this calculation that they're using to compare to ours. But anyway, I'm going to show you guys a quick footage from a flight from New York to Moscow, and then I'm going to go over his other paper. Okay, and then with this paper, it's the turbulent ship wakes, further evidence that the Earth is round. And this was an earlier paper done in 2005. Basically, I'm not going to go into detail here over this. We'll talk about this after we talk about the curvature paper tonight, because it's in line with it. But first thing I want you to take note when you're looking at this is that in the later paper in 2008, he talks about how you have to put that horizon in the center in order to get a true picture of its curvature, right? That if you tilt the camera down, you're going to get the curvature. If you tilt it up, you're going to get a convex. So that right here, this picture that he's using for his evidence is already contradictory of what he says in his other paper. And we'll go over this here tonight about how he presumes that the wake of the ship has to come to a point on flat Earth. Yet down here, his evidence about, because he's using this picture, he's taking this picture, and you can see the little curved dip there because of this bent horizon, because of the camera being tilted. But he uses his evidence there. He calls it a dip, and he goes, there's two things here that prove a curvature, is that the width of the wake, there's width there, and that it dips a bit right there. But he also tells you in this same graph here that the true horizon's way up here. So what if that's the true horizon? Like we know, like Jaron pointed out in his one video, where the birds are coming down and basically diving in the midair above the ocean. So we know there's this invisible area here, not invisible, it could be hazy, it just depends on weather conditions, or conditions with the atmosphere, stuff like that. But we typically know the further down towards the horizon is going to start to play tricks with our eyes, and one of them is this kind of mirage, right? So if we were to take as assumption that the wake should end in a point, if we were to draw this line out, I believe that that makes a point into the true horizon. So this evidence that he was using, and he had the thickness of the wake at the horizon, talking about older ships weren't fast enough and they wouldn't have been able to tell, but they should have. Still had a little bit of a wake still in the horizon that they could have measured, which would have told them it was curved back in the past, which I think is a bunch of baloney, the way he puts it. But the mere fact that he's using a picture that he later talks about that this is incorrect as the basis to this experiment that he's posted only leads to a false conclusion, in my opinion. Again, we'll go over that tonight, and what I'm going to do here is I'm going to play a video of a ship with its wake behind it, so you guys can just visualize what the actual wake looks like aboard. I believe it's just a cruise ship I got the footage from, but we'll go into this article in depth tonight, go through it in detail with you guys, and we'll dissect it and get a good understanding of what the scientists are using to base all their conclusions on and how they came to it. But I'll let you guys go. You guys enjoy this clip, and I'll see you tonight in the stream.